welcome to solving IVPs involving impulse functions. So let's consider IVPs of the form AY double prime plus BY prime plus CY is equal to f of t plus alpha times delta of t minus t naught. With y of 0 equals k naught and y prime of 0 equals k1. We're going to go ahead and assume that f of t is piecewise continuous on 0 to infinity. Then it turns out that we can essentially break this into two problems. One being that basic IVP with impulse function as its forcing function, and the other being just a simple non-homogeneous second order equation or second order IVP. So I claim that if y hat is the solution to AY double prime plus BY prime plus CY equals f of t with initial conditions y of 0 equals k naught and y prime of 0 equals k1, and y bar is the solution to the IVP AY double prime plus BY prime plus CY is equal to delta of t minus t naught with initial conditions y of 0 equals 0 and y prime of 0 equals 0. So namely, y bar is u of t minus t naught times w of t minus t naught, where w is the inverse Laplace transform of 1 over the characteristic polynomial as squared plus bs plus c. Then if we're in this situation, then y of t equaling y hat plus alpha times y bar is the solution to our original IVP, or is a solution to the original AY double prime plus BY prime plus CY equals f of t plus alpha times delta of t minus t naught with the initial conditions y of 0 equals k naught and y prime of 0 equals k1. So essentially the problem boils down to, if we want, we could solve two separate IVPs. The second one, we already know the solution to. That's what we did in the previous video. The first IVP, we certainly have the techniques to solve at this point. So just for a very quick sort of proof sketch. If we do A times y hat plus alpha y bar double prime plus B times y hat plus alpha y bar, taking just this first derivative, plus C times y hat plus alpha y bar. This is equal to A y hat double prime plus b y hat prime plus c times y hat plus alpha times a y bar double prime plus b y bar prime plus c y bar. That alpha is multiplying all of the stuff involving y bar. This a y hat double prime plus b y hat prime plus c y hat was equal to f of t by design. The a y bar double prime plus b y bar prime plus c y bar is by default equal to delta of t minus t naught. And so we have alpha times delta of t minus t naught. So we have that the equation is satisfied. Again, those two simplifications are because y hat is the solution to the ay double prime plus by prime plus cy equals f of t. And y bar is the solution to ay double prime plus by prime plus cy equals delta of t minus t naught. Furthermore, if we want to do y hat plus alpha y bar evaluated at 0, that's y hat of 0 plus alpha y bar of 0, which is k naught plus alpha times 0, or k naught. Similarly, we can do the same for the second condition. I'm going to give myself a little more space. Now I'm doing the same for the second condition. We have y hat plus alpha y bar, taking the derivative of that, evaluated at 0. This is y hat prime plus alpha y bar prime, all evaluated at 0. That is y hat prime evaluated at 0 plus alpha times y bar prime evaluated at 0. And by our initial conditions, y hat prime evaluated at 0 was k1. And y bar prime evaluated at 0 was equal to 0. And so we wind up just getting k1. So we have the equation and the initial conditions are satisfied. So y equals y hat plus alpha y bar satisfies the IVP. So let's go ahead and do a quick example. So let's take the IVP y double prime plus 5y prime plus 6y is equal to e to the negative t plus 3 delta of t minus 2. With initial conditions, y of 0 equals 3 and y prime of 0 equals negative 6. Now, if you wanted, you could just take the Laplace transform of the entire equation and solve that way. Or we can use one of our other techniques. So let's go ahead and split into two IVPs. So the first one will be y hat double prime plus 5y hat prime plus 6y hat equals e to the negative t, with y hat of 0 equals 3 and y hat prime of 0 equals negative 6. So if we find our characteristic equation, we're looking at r squared plus 5r plus 6 is equal to 0, or r plus 2 times r plus 3 equals 0. We get r is negative 2 or negative 3. So we know our homogeneous solution y hat c is c1 e to the negative 2t plus c2 e to the negative 3t. Our non-homogeneous solution, I'm going to run method of undetermined coefficients. We have our guess will be yp, or y hat p, is a e to the negative t. This has no conflict with our homogeneous equation, and it does, or homogeneous solution, and it does match our forcing function. So we have yp prime, or y hat p prime, is negative a e to the negative t, and y hat p double prime is a e to the negative t. So we are looking at a e to the negative t plus 5 times negative a e to the negative t plus 6 times a e to the negative t should just be equal to e to the negative t. Matching coefficients, this means that a minus 5a plus 6a, otherwise known as 2a, should equal the 1 in front of e to the negative t. Or in other words, 2a e to the negative t should equal e to the negative t. We get therefore that a should be equal to 1/2. So we have that our y hat should be equal to c1 e to the negative 2t plus c2 e to the negative 3t plus 1/2 e to the negative t. From here, we need to solve for c1 and c2, right? So plug in the initial conditions. And we are looking at y hat of 0, which is just c1 plus c2 plus 1/2, should be equal to 3 or in other words, c1 plus c2 is equal to 5/2. For y hat prime of 0, y hat prime of t, we're looking at negative 2c1 e to the negative 2t minus 3c2 e to the negative 3t minus 1/2 e to the negative t. Plugging in 0, we have negative 2c1 minus 3c2 minus 1/2, and that should be equal to our second initial condition was that that derivative was equal to negative 6, or negative 2c1 minus 3c2 is equal to negative 5/2. So we are working with a system c1 plus c2 is equal to 5/2. Negative 2c1 minus 3c2 is negative 5/2. If we multiply that first equation by 2, positive 2, and add them together, we are looking at the c1s cancel. We have negative c2 is equal to 5/2. Or c2 is equal to negative 5/2, assuming I did that correctly. If we multiply that first equation by positive 3 instead, we would be looking at positive c1 is equal to 5. Let's just check that I did that correctly. That does not look correct. What do we have? C1 plus C2 is 5/2. negative 3C2. Let me just check this, make sure I find where I made my mistake. I apologize. Negative 6 plus a half is not 5 halves. So this should be negative 11 halves. There we go. Which would also change here. This should say negative 11 halves. Therefore, we have negative C2 is equal to negative 1/2. Or C2 is equal to a positive 1/2. Apologize. I make careless arithmetic errors every once in a while, as I'm guessing all of us do. If we do fixing for C1, we have negative 2C1 plus 3C1 gives us C1, and then we would have negative 11 halves plus 15 halves should be 4 halves. So C1 is equal to 2. Again, I apologize for the algebra error or arithmetic error in this case. We wind up getting here that our y hat should be equal to 2e to the negative 2t plus 1/2 e to the negative 3t plus 1/2 e to the negative t. The second problem that we were supposed to solve, second IVP, was y double prime plus 5y prime plus 6y is equal to delta of t minus 2, if I remember correctly. I apologize for the scrolling. Yes, delta of t minus 2. This one, our initial conditions are just our y of 0 equals 0 and y prime of 0 equals 0. And we know that this has solution. Y of t is equal to u of t minus 2 times w of t minus 2, where w of t is the inverse Laplace transform of our characteristic 1 over our characteristic polynomial. So 1 over s squared plus 5s plus 6. We can factor that. We are looking at the inverse Laplace transform of 1 over s plus 2. 1 over s plus 2 times s plus 3, all in the denominator. If we do partial fractions, we are looking at the inverse Laplace transform of, we will have something over s plus 2 plus something over s plus 3. Solving those quickly on the side, we have a over s plus 2 plus b over s plus 3 equals 1 over s plus 2 times s plus 3. That becomes a times s plus 3 plus b times s plus 2 is equal to 1. If we set s equal to negative 2, then we are looking at a times 1 equals 1, and therefore a should equal 1. If we set s equal to negative 3, then we are looking at b times negative 1 equals 1, and therefore b is negative 1. So we are looking at the inverse Laplace transform of 1 over s plus 2 plus negative 1 over s plus 3. So we have w of t is equal to e to the negative 2t. And then minus e to the negative 3t. Again, 1 over s minus a goes to e to the at. So here our a's are negative 2 and negative 3, so that we have a minus negative becoming positive. So we have our w of t. Then we can find w of t minus 2. We're just going to replace all those t's with t minus 2. So we have negative e to the negative 2 times t minus 2 in the exponent, minus e to the negative 3 times t minus 2 in the exponent. So we get that our y bar of t is equal to u of t minus 2 times e to the negative 2 t minus 2 minus e to the negative 3 times t minus 2. So putting this all together, our original equation we had e to the negative t plus 3 delta of t minus 2. So our alpha here is 3. So we have solution y of t is equal to y hat of t plus 3 times y bar of t, or y of t is equal to 2e to the negative 2t plus 1/2 e to the negative 3t plus 1/2 e to the negative t plus 3 u of t minus 2 times e to the negative 2 times t minus 2 in the exponent minus e to the negative 3 times t minus 2 still in the exponent. If we wanted, we could write this in piecewise format. So we have until t equals 2, we just have that y of t is that first component, 2e to the negative 2t plus 1/2 e to the negative 3t plus 1/2 e to the negative t. This is for 0 less than or equal to t less than 2. Once we hit 2, we add on the remaining component. So we have 2e to the negative 2t plus 1/2 e to the negative 3t plus 1/2 e to the negative t plus 3 e to the negative 2 times t minus 2 minus 3 e to the negative 3 times t minus 2 for t greater than or equal to 2. If you wanted, you could do some manipulation with those exponents to sort of combine terms. Technically, we could rewrite this second component here as a 2 plus 3 e to the 4th, all multiplying e to the negative 2t. Then we could have a 1/2 minus 3e to the 6th, all multiplying e to the negative 3t, and then a plus 1/2 e to the negative t, if you like. I apologize, my screen's not updated. So again, we have essentially, I just did e to the negative 2t times e to the 4 and pulled out that 3e to the 4th, or pulled out the e to the negative 2t, that left us a 3e to the 4th. Similarly, I did e to the negative 3t times e to the 6th, pulled out that e to the negative 3t, we were left with a negative 3e to the 6th. So this is just an alternative way to write that second component, again, for t greater than or equal to 2. So the impulse function just kind of adds in a little bit extra once we hit that t equals 2, it just sort of kicks the equation a little bit. Or adds a new component to the solution. But this is solving IVPs using the split method. Again, with an IVP, it may be just as fast to simply solve by taking the Laplace transform of the entire equation and taking that route. So it's entirely up to you which route you take. This is one possibility.